In this video, I'm going to take you behind the scenes of how I made 2D Minecraft inside a chest. Just in case you haven't seen the main showcase video already, make sure to watch that one first so you actually know what's going on. But this video is just for anyone who's curious about more of the details of how everything works behind the scenes. All in all, ChestCraft is made with custom code that runs on the server side in the form of a plugin. So a plugin is something you can very easily add to multiplayer servers, and it means that players who join don't have to install anything. The code runs only on the server. This does create a lot of limitations on what's actually possible, seeing as you can't change the code that's running on the player's computers, only what's on the server. So yeah, making plugins involves constantly working around those limitations and trying to make the most out of what is possible with the existing game code. And yeah, ChestCraft is no exception to that. But what is this server-side code actually doing? Well, it's basically a complete recreation of Minecraft from the ground up, with over 25,000 lines of code so far. The majority of the code is exactly what you'd write if you're just making a standalone 2D Minecraft ripoff, and there are just small sections of input and output code which actually link to the real Minecraft game this is running inside of. So standard plugin code is used to detect inputs like clicking in the chest, and those are passed into the bulk of the game code. And then 20 times a second, output code updates all of the items in the chest to reflect the state of the simulated world. Lots of the internal workings of ChestCraft are actually inspired by how Minecraft itself works. So concepts like chunks, entities, loot tables, and behavior trees are all things from the vanilla game code that I've also used. And actually, when I'm trying to recreate some kind of complicated mechanic like explosion damage or something like that, I often end up looking through the actual Minecraft game code to extract kind of the useful formulas and algorithms, because the Minecraft wiki often just doesn't have enough detail. But as you may know, Minecraft is not actually open source, so I can't look at the actual source code, and instead I have to work with this kind of reverse engineered decompiled code, which lacks a lot of useful things like comments and variable names. Like you can see all these variable names are completely useless and they're just like single letters. So trying to actually understand what any of the code does is a bit of a pain, but sometimes worth it. And then the other crucial aspect of ChestCraft is the saving and loading of data. So ChestCraft has these special folders it creates inside the server, one for each world and one for the player data, and in there it stores custom saved chunk files, custom saved player files that store everything about the state of the world, so that when the server stops and restarts, everything comes back exactly as it was. But it's not all about code. Resource packs are actually really important for ChestCraft. So most people think of resource packs as just a way to change the textures of stuff in game, but you can actually use them to do quite a lot more than that. So what you're able to do is you can take a single item, like in this case I've used white dye, and you can use a feature called custom model data, which basically allows you to set this invisible property on an item, which is just a number, and it can be from 1 to whatever you want. And depending on what that number is, a different model will be used for the item, which is looked up in this big table here. So here you can see I've set up, hundreds, and actually it goes all the way up to 2,300 different models that can all be used by the same item. So this lets you add basically a bunch of whatever you want into the game without actually overwriting anything. So I'll show you in game here. These are all my chests, which are full of all of these custom items, and you can see what I use them for. So all of these are actually just white dye, but set up to look like something else. So you can see they're used for menus, this is the furnace stuff, and then they're also used for things like animated blocks, so like the chest opening. I've just made these different animation frames which can be swapped between. Then crops, or stuff like that. There's obviously no actual item in the game that looks like this, so these are all just added with resource packs. You can see crops, cake, blocks with animated textures, fluids, which we'll come on to more later, fire, just loads of animated stuff, animations for the enchanting table book that gets up and flips around. Yeah, and it goes on and on and on. There's all the animals as well, which I'll talk more about later. But yeah, the general idea is resource packs are very useful in allowing you to add in these things that are actually just white dye, but they can look like basically any 3D model you want. So you might be wondering how I actually make all of these models, and the answer is this useful piece of software called Blockbench, which is basically a tool specifically designed for messing with Minecraft resource packs. So it allows you to just add various different cubes and add textures to them. So I can just steal the textures from the vanilla Minecraft game and then just, add a few cubes in the right place, set up the textures, and then I can manually rotate stuff around and save different frames of the animation and stuff like that. And mobs are kind of the same story. Again, I can steal the texture file from the vanilla game, and then it's just a matter of, setting up all of these bones in the right position. And obviously also I have to control how the item displays in a Minecraft slot so that it actually looks right in the ChestCraft inventory. But that's all stuff that can be done with the resource pack settings, so I can move this around. There was a bit of a challenge for mobs, which is that the models for Minecraft mobs are not saved in any useful format in the game data. They're actually just kind of hard-coded into the code. For a skeleton, for example, these are where it sets up its arms and legs, and it's basically just like a list of coordinates. But I had to just go through the code and interpret these coordinates and actually translate that into Blockbench. So it was quite a lot of effort in making the mobs, but it's worth it because I think they look absolutely amazing in game. And obviously you have to create versions of them that are flashing red, versions of them that are facing left, facing right, all of the bow drawing animations for skeletons, stuff like that. So it was definitely quite a long process, but well worth it for the final in-game result. The other cool thing that I was able to do with resource packs is make these dropped items. So I made a miniature version of every single item in the entire game. You can see these, they're just like a shrunk down version. And there are chests and chests full of these. There's literally one for every single item that exists. And yeah, these could be used to represent items that are dropped on the ground. And as you might expect, I didn't want to make all of these manually. There's hundreds of them. So I actually wrote some code to do this for me. It's just a quick little hacky thing, but it takes all of the JSON files that represent the data behind items and blocks, and these are all taken directly out of the vanilla game files, and it just runs a fairly simple process to create a resource pack version that's essentially the same but smaller. So yeah, I was able to use that. It took a while to figure out how to make this work, but once I got it done, I could run it once and instantly generate the resource pack version of every single one of these items, and I think they look really cool. And yeah, honestly, that's the best way I could think of to represent items dropped on the ground and distinguish them from, blocks that are placed and stuff like that. And I think it works out pretty nicely in game. Although not every block and item has its full functionality yet, I have in a basic sense added every single block and item to the game, minus these ones in red that I decided don't really actually make sense to have in ChestCraft. By this I mean that the game knows all of the basic properties of these blocks and these items, such as the sounds they make, what tools you need to mine them. For items, it's stuff like if it's a food, how much hunger does it give you, whether or not you can use it as a fuel in a furnace, that kind of thing. And in the code, what I've ended up with is these horrendous files that have a line of code for every block, which stores all of these properties, and the majority of this was just done manually, getting the information from the Minecraft wiki, which took quite a few hours. And you might think that I could get all this information directly from the Minecraft code, but it turns out that in the vanilla Minecraft game code, they don't store all of this in one convenient place like I wanted to do it, and it's kind of scattered around everywhere. So there probably would have been a way to gather everything, but in the end I decided it would just be easier to do it semi-manually. So that's what I did. And here's the equivalent for items, which is a bit simpler because most items don't really have that much going on, and it was just a case of adding information specifically to the items that needed it, like the fact that an oak boat can smelt 6 items in a furnace, all that kind of thing. Another interesting thing to talk about is crafting recipes. So back in the early days of ChestCraft, I was just adding crafting recipes manually. So for something like a wooden pickaxe, I would just have to specify, okay, you have oak planks, oak planks, oak planks at the top, then nothing, a stick, nothing, nothing, a stick, then nothing. And I just make something like this for every single recipe, and this is the code from back a couple of years ago when there were barely any items. And as you can see, it wasn't too much effort to just add these manually. But obviously Minecraft has a lot of items, I don't really want to do this forever, and it turns out there is a much easier way, because Minecraft itself actually stores all of its crafting recipes conveniently in these JSON files. So for example, if we go to wooden pickaxe, you can see here is the overall shape of the recipe, and it's just a little key-based thing where the X is a planks and the hash is a stick. These files just come with the Minecraft game, and there's one of these for every single possible crafting recipe. So instead of all this code, I just wrote code that can read all the recipes. So the code is a lot more complicated, and it has to handle things like, you might have noticed in the file, it just said planks, not oak planks, because obviously you can make a pickaxe out of any planks. So somewhere here I have to add in my own little code to say that, okay, if it says Minecraft planks, that actually means it could be any of these. And also there's quite a few different types of recipes. So for example, some crafting recipes require a specific shape, like a wooden pickaxe, and some crafting recipes just require you to have the correct items in whatever order, like a flint and steel. You can just put an iron and flint wherever you want. So each of these different types of recipes have a different format in the JSON file, so they all require a different code to load in. There's also furnace recipes, so there's like smelting, blasting, smoking recipes. So I wrote code to load those all in as well automatically so that you can do all the normal stuff in a furnace you would. But this is pretty nice using all the JSON files, because the vast majority of recipes in Minecraft are now just automatically in ChestCraft without any kind of manual work needed. So that was pretty cool. One thing I definitely want to talk about is the fluid system. So that's water and lava. So yeah, ChestCraft has fully working water and lava, and this was just definitely one of the most difficult things to set up. So yeah, I wanted to go through a little bit of the details behind that. So first of all, we just have the actual graphics themselves. So I've got all of the different water and lava items. So each of these is just a piece of white dye with a animated texture, and there's all the different combinations of different flow heights and different flow directions and stuff like that. So the way that animated textures work in Minecraft is you basically have a very tall texture that just has the same thing repeating vertically, but with a slightly different frame each time, and the game will just cycle through each of these frames, and it's kind of hard to tell between these, but the patterns of the water are slightly changing, and when you play through these you get the flowing animation. So I started out by just taking the water texture from the vanilla game, which just looks like this, and then I basically just had to, in Paint.net, just go and cut out little triangles. I obviously did it a bit more precisely than this. I was actually, counting the pixels and stuff to come up with these kind of textures that have the actual flow gradients. And then I just had to do this a whole bunch of times to make all the different possible combinations. And in the end, this is what you get. You get these nice animated textures that join together. But yeah, when it comes to actually doing the code for this, it's a lot more complicated. So one thing I ended up doing was I would take barrier blocks and I would just set up a little enclosed single strip of a Minecraft world, and that way I could just go and place down water, place down lava, place down some blocks, just make these test scenarios and just try and wrap my head around how do Minecraft fluids behave in this, simple 2D environment. The fluids kind of sense out in both directions and work out which way to flow. There's all these rules for merging different streams of water, all that kind of thing. So yeah, I spent a while just wrapping my head around how this worked, and then I moved to actually trying to tackle it in the code. And in the end, this is what I have to show for it. It's just 400 lines of fluid code, roughly, all in all. And although that's not really that much, these 400 lines took a very long time to write and get fully working. It was kind of a case of, try some stuff and then go into Minecraft, build some kind of test scenario, recreate it in ChestCraft, and see if the behavior matched up. And normally it wouldn't for various reasons. I'd have to go through and try and fix all the bugs and actually get the fluids working properly. And yeah, there's a surprising number of edge case scenarios that you wouldn't think of. And yeah, in the end, it gives a pretty nice effect in game of you can actually just have functioning water and lava. And yeah, well, once I got this finally working, and it just looks like how Minecraft water behaves, because it is in fact how Minecraft water behaves. So yeah, it was very satisfying to get done in the end, but definitely one of the biggest challenges. So yeah, that was fluids. I mentioned earlier how plugin development often requires creatively working around the limitations of Minecraft, and I think the best example of that in ChestCraft is probably the day-night cycle. The time of day is pretty important in Minecraft. You need to know when monsters are going to be spawning and stuff like that, so I really wanted a way to represent this in ChestCraft, and having the sky actually go dark would be ideal, but there isn't any obvious way to dynamically change the background colour of a chest. But, as you can see here, I have actually managed to make this work. The secret lies in some sneaky resource pack abuse. Some of you may have noticed this cross marking out an unusable slot in the inventory, and that's actually how the sky works. When you're using resource packs to make custom item models, there's nothing that says that the model for an item has to actually fit within a single slot. You can make them a lot bigger. So this is what the item actually looks like. You'll see it's got just this little cross and then also the big dark rectangle that makes the sky. And you'll notice that when I put it in this exact slot in the inventory, it exactly fills out the chest. Crucially, I have to make all other items render on top of the background, otherwise it would be blocking them out like this. And if I open up the item in Blockbench, I can show you how that works. So in this display tab, you can see I can use these sliders to change the position of where the item renders in an inventory slot. But it also has this Z-axis slider, which doesn't seem to do anything because items in the inventory render without any perspective. But if I set this value all the way to the minimum of -80, that puts it as far back into the inventory as is possible, and that ends up meaning that all other normal items will render on top of it, which is what we need. The other piece of the puzzle is then just creating 180 different variations of this item, each with a slightly different translucency value, so that for sunrise and sunset, you can transition smoothly between day and night by just swapping between these items gradually. So this one I've got here is the one that's most dark, and here you can see one that is much lighter. There was a problem though. When I open something like a crafting table at night, you can see the sky background inside of the menu too, which just looks really bad. To fix this, I had to create different variants of the sky item with different shaped holes in it, like this one for the crafting table and this one for a single chest. And now the crafting table looks much better at night. I was able to do something similar to this to make this really cool death screen that you see. So you notice that you can still see the entire world behind, but you have this really nice red gradient overlay and then these buttons on top. So I use a very similar trick here. You can see that this item, when it's put in this same inventory slot, makes this nice red gradient that perfectly covers the screen, but would still allow every item to be seen behind it. And in this case, I set the Z position to be all the way to the top instead of all the way to the bottom, so that we actually get all the items in the chest rendering behind. And for the buttons, well, I wanted the world behind the buttons to still be visible. So instead of making the buttons items that are actually set in these slots, they're actually set to render really far above the items so that I can put the respawn button here actually in the player's inventory and the title screen button down here in the player's inventory, but they still render up here in the main screen. The overlay for when you're going through a nether portal is another interesting one, especially because I wanted to make it work in conjunction with the sky, so that if I set the time to night, you can see that the background stays dark even with the overlay. The way I did this was quite interesting. I have this item here on Blockbench that has the sky grey rectangle down as far in the vertical direction as it can go, and this nether portal overlay as far up in the vertical direction as it can go. And when you look at this front on, you just see a single rectangle that's just kind of a dark version of the nether portal. But when this actually gets rendered inside the Minecraft scene, any normal blocks get rendered above the sky background but below the nether portal overlay. And obviously I just used an animated texture for this, which is just taken from the Minecraft game files. The final thing I wanted to talk about was procedural terrain generation. This was definitely one of the biggest challenges I faced, and I put off working on it for a really long time. And almost all the other features I've shown you were created when we still just had super flat terrain. This is an area where I don't really know what I'm doing, so I ended up just making up a lot of stuff as I went along. And I'm probably not doing things in the most conventional way, but I am pleased that I've got an end result which works pretty well and is actually my own work. The thing you're seeing here is a standalone bit of software that I created for working on the terrain generation, since the little 9x6 view you get inside a chest just isn't good enough to get a sense of the actual terrain. So I just created this simple program that just renders blocks as basic colors, and here is a big list of a bunch of variables that are used in the code, and any of these you can change and the result will update in real time. So for example, the seed, I can just change this and get a completely different world, and all of these other variables are specific things to do with the terrain generation that I could tweak in real time and see the results. Some of you might be wondering what's actually so hard about terrain generation. The challenge comes from the fact that the ChestCraft world needs to be essentially infinite, which means you can't just generate it all at once, and you have to do it just like Minecraft on a chunk-by-chunk basis. This means any individual chunk needs to be able to generate without any knowledge of the chunks to either side of it, because those might not have been generated yet. But obviously the end result still needs to be smooth and continuous. The answer is to use mathematical functions. Take this sine wave for example. The height at any given point is generated by just taking the sine of the x value. So each point can generate without having any knowledge of what's on either side of it, but the end result is still smooth. Obviously sine waves won't make for great terrain, but we can use the same kind of concept. Perlin noise is another mathematical function that has the same kind of smoothness properties, but looks a lot more random, so that's what we'll use. One thing I did already know about terrain generation is that the secret to good terrain is to add up multiple layers of Perlin noise, each with different frequencies and amplitudes. For anyone who doesn't know, the frequency is just how rapidly the terrain changes as you move along, and the amplitude is how vertically extreme the changes are. We can visualize this by using this desert-only world. Over here, I've set up the frequencies of various noise layers, varying from high frequency down to lower frequencies. And these settings here let me control the amplitude of each layer, and they're all zeroed right now. So if I first raise the amplitudes of individual noise layers, then you can see what they each do. And you can see that as we go up, we get progressively higher and higher frequencies, up until these fine details, which are super high frequency. If I now take these back to their default values, you can see that by using progressively lower amplitudes of higher frequencies, we can gradually build up better and better looking terrain until we get an end result which looks something like this. You can see as well now why being able to instantly visualize changes in these variables is super useful, because it means that I can actually figure out what these values should be just by playing around. There's another interesting detail that I came up with before we move on to talk about biome blending. You might notice that these two layers, hills and rarer hills, I'll show you this is rarer hills and this is hills. They have the same frequency, they're both 0.4, but they obviously have very different behavior. The secret to create these rarer hills is to pass the Perlin noise output through some kind of non-linear activation function, and I'll show you what that actually means. So we start out with just a high amplitude Perlin noise layer. So this creates plenty of big hills, but it also creates these massive dips as well, which we don't want. The solution is therefore to multiply the noise by 0 at any points where it's negative, which basically just cuts out all of the valleys and only keeps the hills. This still leaves us with quite a lot of hills of varying size, and I actually only want to keep the big ones. So the solution is to take all of these noise values, and any ones that are less than some threshold, which I've got here, we can multiply again by something. Now I could just multiply them by 0, which would cut them out completely, but I ended up going for 0.2 to make things a little bit less harsh. Now we can actually visualize this activation function, which our noise outputs are being passed through, and you can see the 3 different sections here. And we can compare this to just the simple linear case, which is what most of the other noise layers are using. Everything I've said so far only really works for a single biome. As well as using different blocks, different biomes also need to have different kind of terrains. My main idea of how to do this was to use the same noise layers for each biome, but let each biome have its own unique set of amplitudes for each of those layers. This works totally fine within each biome, but there's a big issue at the boundary. I needed a way to smoothly blend between biomes, and my idea here was that if the amplitudes of the noise layers transitioned smoothly instead of just jumping, then the terrain would also transition smoothly. My first idea was to use a rolling average. Let's say this red line represents the amplitude for one of the noise layers, which changes suddenly between these two biomes. Now what I'll do is I'll roll this purple box along, and the value of the blue line at each point is calculated as the average of all of the red line values within the purple box. As you can see, when I go over the interface, we get this linear transition. This may seem like a convoluted way to create a straight line, but the good thing about it is that it generalizes nicely to the scenario where we might have multiple biome transitions within the width of the rolling window. As you can see, what happens here is we still get a linear pattern, but with multiple straight lines, and that would be a lot more difficult to calculate. When we implement this in-game, you can see it does create a transition between the two biomes, but it looks very linear. Remember, we're not directly doing the rolling average of the terrain height, but instead of the noise amplitudes, so the result isn't actually perfectly linear, but in a lot of cases it still very much looks like it, and it doesn't look great. The way I came up with to fix this is to use a weighted rolling average instead of a normal rolling average. By giving a different amount of importance to different parts of the purple box, we can break the linearity. My idea was to use a normal distribution, which is also known as a bell curve, to weight the average, which gives more importance to the stuff in the centre and less to the edges. Now you can see that as I slide this along, if you ignore the low frame rate, it gives a much smoother transition between the two biomes. And of course, it generalises nicely to more complex situations with multiple boundaries too. If we now go in game and use this normal distribution method, you can see it makes the transition much less linear and much more natural. There are many other aspects of the terrain generation that I haven't touched on, like these subsurface layers or tree generation, but I just wanted to give an overview of how this works and show why it was such a challenging task. And that's it for this video. I didn't have time to explain everything, but if you have any questions, feel free to leave them in the comments. Thanks for watching.